Our next speaker is Andrew Glascott-Jones, Field Applications Engineer, Teledyne, e2v Semiconductors, France. Ladies and gentlemen, please extend a warm welcome to Andrew Glascott.
Thank you very much for inviting me to speak to you today. It's humbling to be here. This morning, it kind of hit me home that all the achievements that the Indian Space Agency and the Indian ISRO and those guys have done. It was quite emotional morning. So thank you very much for inviting me to speak a little bit about my experience in the space industry and what we do and what Teledyne e2v Semiconductors does. I'm a field application engineer for Teledyne e2v Semiconductors, and my job is to help customers use our chips. We're a semiconductor company, we produce chips, and my job is to help those people use those chips in their applications and to understand their applications. Our market is in the high reliability market. And so that means that a great many of my customers are space customers. So I'll try to give some examples of where outsourcing, I've seen examples of outsourcing where it's worked. I'll give a little introduction about Teledyne in global, and then some more details about Teledyne e2v Semiconductors. I've got a couple of slides about my view of the space market in Europe and how outsourcing helps that market, where it can hinder it a little bit, and the rationale behind outsourcing in the space market in Europe. And then a little bit more detail on Teledyne Semiconductors, what we do, the kind of products that we produce, and what kind of applications we go in, and then a quick summary. So here's globally Teledyne in space since the 1960s. It was on first the Apollo missions, produced hybrids as part of the Apollo missions. Then we were on the space shuttle with hybrids as well. Also geospatial imaging pods, the special build by part of Teledyne that did special systems. Also on the Hubble Space Telescope. And then part of the product line that I'm involved with, that's Teledyne e2v high-rel electronics. Well, they have specialist space-grade RF components. And so they were used on some scientific experiments that flew in the 2000s. And then we come right the way through to a more module, a subsystem effectively, which you can see there, number 10. And I'll speak a little bit more about this on the next slide. But that's for the OneWeb constellation. So that's another part of Teledyne that has produced subsystems for the OneWeb constellation. And that's an example of where outsourcing and the new space market has helped that particular part of Teledyne to grow. Now, this slide is a little bit focused on part of the Teledyne organization that isn't so much involved with the products that come out Teledyne e2v Semiconductors. So I've added in here the effect that where some of our products have been used. And you can see these two devices here. That's a high-speed DAC, 3 gigasample per second DAC, and a high-speed ADC, both space grade. The ADC is 1.5 gigasample per second, and now they've been sold in their thousands, FMs in their thousands, and they're in pretty much every high throughput satellite that's flying now, and they're being designed into the next lot of high throughput satellites, and also Earth observation, synthetic aperture radar systems as well. So these are really great products, and they're heavily used in traditional space systems. And we're working with ISRO using these components as well. And then we are introducing gigaflop processors for space applications as well. So these are new application areas. And I won't go through the product line, but I'll give you some ideas of where we're going in those particular product lines. Now this is the company that I was speaking about. They're based in the UK. They're part of the Teledyne organization. They're part of Teledyne Defense and Space. And they were experienced in RF small filters, RF subsystems, some electronic warfare systems. And then, thanks to outsourcing, thanks to the new space market, and I've got a definition that's from actually the director of marketing of this company, and he says the new space market for him is customers' willingness to negotiate some risk on the individual subsystem for a reduction in cost, and a willingness to negotiate with somebody who hasn't got space heritage. So from this company's point of view, they negotiated and they won a bid for a part of the OneWeb system, and that was, I think, 2016, 2017. What you can see from, this is a slide that the director gave me, this part of the slide here. And in 2017, their market, their space market, was that small circle. And thanks to that, and thanks to an expansion in capability and investment, they now can look for business in a much wider area. So there's one of the positive aspects of outsourcing and the new space market. So enough about another Teledyne business unit. Now we'll speak about my Teledyne business unit. I'm Teledyne e2v Semiconductors, and we produce semiconductors for high-rel applications. Our strategy is, in the main, that we partner with other companies who have already produced the component, the silicon, the gallium arsenide, whatever, and we screen it, qualify it, repackage it, and produce it for high-rel applications, civil avionics, military systems, and space. And our partner companies, NXP, Peregrine, ISSI, GaN systems for power FETs, some memory companies as well. The one part of our IP portfolio that we design ourselves are the data converters. And that team is based in Grenoble in France, where I'm based as well. So we provide this range of products for high-rel applications and have a wide footprint in the space market. Now, I've got some slides here that are my view of the space market in Europe, and they're based on my interactions with these companies. I've certainly missed some companies off, and I maybe have put a company in the wrong tier, but it's just to show that the way the kind of food chain operates, and there's an equivalent diagram that I've got for the new space market, which is slightly different. So you can see the final client up at the top. That can be, if it's a telecom system, it's one of the big telecom operators, Inmarsat, Eutelsat, SES. Final customer could be ESA for one of their space probes, Flex, JUICE, Prober. So they commission the scientific mission. Or it could be governments for their military satellite, military telecommunication satellite, or Earth observation satellite. And in general, those final customers will look at a prime to be the prime. And in Europe, there are three primes: Thales Alenia Space, Airbus, and OHB. Probably Thales Alenia Space and Airbus are the major primes in Europe. And in particular, for the telecoms operators, they will look to the primes in Europe, but they'll also look to the primes in the US. So they'll also be looking at people like Boeing and Space Systems, Laurel, and those kind of people. So once the project's been negotiated and it's in the prime, then the prime will be looking at individual subsystems. And a gentleman earlier today from ISRO gave some indications that was also the case in ISRO, that strategic equipment would be designed in-house, and less strategic equipment could be subcontracted out. And that's often the case with the primes. So they will go to other companies like RUAG in Austria or Sweden, Leonardo in Italy and the UK, or Kongsberg in Norway, to do subsystems like data links, up-down converters, and frequency generation, that kind of thing. Surrey Satellite Systems, that's an interesting company because they kind of almost started the new space market a while ago, and they're now part of the Airbus group, and they're sometimes a prime. They've been a prime for some satellites. I think Quantum Telecommunication Satellite was built by SSTL. And then below the tier 2, these are companies that will have a specific experience, a specific ability in a particular domain. For example, Terma, ASP, they're really good space-grade power supplies. Antwerp Space, Data Links, Omnisys, that's scientific experiments using microwave receivers, that kind of thing. So that's the way the food chain goes in the traditional space. And then in the new space market, and here's the quote from my friend, the director at Teledyne Microwave in Shipley. So for him, new space, there are lots of different definitions of new space, but for him, it's a willingness to negotiate risk for a cost reduction for a particular system. Obviously, in a constellation, although the risk for one of your satellites is higher because your components haven't been screened so much, because you've got so many satellites spinning the Earth, it doesn't matter if one goes down. So for the overall system element, the risk will be acceptable. But for a satellite in that constellation, the risk that it fails could be higher. It's interesting here that from what I see, the final client, well, we've got SES, they're producing O3b, with OneWeb, Telesat. Some governments, that's the Italian Space Agency, they've commissioned a kind of a new space satellite, and that's really to show off the capability, and they've contracted it out to Italian companies, and that's to show off the Italian space competence with this, I think it's 2 or 3 satellites called Platino. So some governments do get involved through their space agencies. I won't go through a lot of this, but the point is that here you can see Sealinks. That's a French company that was producing data links for avionics systems. Now, that was able to move into the space arena thanks to the new space market. Otherwise, it probably would have stayed where it is. So there's an advantage there in the new space market, bringing in new companies. And also, we see Sideral there. That's a traditional space company, and also a new space, in the new space market, and we see the same, RUAG and Kongsberg are also in that market as well. So, now, a bit more information about Teledyne Semiconductors. As I said, we produce a range of components from RF components using Peregrine space products. I've got a slide that shows that very quickly later. Power solutions for the space market. High-performance processors based on a partnership with NXP. And we design ourselves the ADC and the DAC. Here's a highlight. It gives you some idea of what we do with high-speed data converters. This is our most recent ADC. It's a quad 1.6 gigasample per second 12-bit ADC with a serial interface. And this is space grade. It's also in the same package. It's also an industrial grade part. So here we can with this part and different levels of screening, we can produce something that will go in a 15-year mission, or we can produce something that will go in an oscilloscope. So that's the strategy that we have to try to bring together the requirements from different markets. And technically, we can interleave the 4 cores. It can go up to 6.4 gigasamples per second. The real highlights for it are that it's got the synchronization feature that allows a multi-element system of ADCs to be very easily synchronized without any external components. So the synchronization signal can travel from ADC to ADC. That's not like that in systems that are around right now. There needs to be a fan-out chip to do that job. So with this synchronization feature, we can take away that chip and reduce system cost and reduce system power as well. And the other interesting feature of this chip is the serial interface. We've not gone with a traditional serial interface for high-speed data converters, which is known as JSD 204. We have developed a protocol that we call eStream, efficient serial interface for high-speed data converters. And the advantages are it uses less resource than the FPGA. You could compare there, a fifth of the resource on a transmit and a third of the resource on receive. And so that has an impact on the power of your system and also of the resource required in the FPGA. So it goes a long way to making systems less power hungry and more efficient. And the other direction that we have with our data converters is that we want to expand the frequency that the data converter can operate in. That's the analog frequency. This means the strategy here is to put the data converter as close to the antenna as possible. For an example, we have a DAC that right now can convert signals from baseband using the alias feature, the aliasing phenomenon, right the way up to K-band. And when you've got something like that, it means that this part, you have a traditional system that would have an up-converting mixer, a local oscillator. You don't need it anymore. You can cut that out, and all you need is a bandpass filter around the signals of your interest, and then the standard power amplifier, and the signal goes out. So you can do a direct conversion to K-band, and that's got advantages of flexibility. You reduce the size of your PCB, you reduce the number of components, that improves the reliability, and you reduce the power of the system. So this is the direction that we are going with our data converters. I've not put a product list up there, but it should give you the highlights and where we're going. On the processor side, what we're offering now, this is based on the partnership we have with NXP. We are offering NXP processors based on either PowerPC, the first two up there, then the second two on the left, they're PowerPC-based parts as well, and the newer processors from NXP are based on the ARM core. And the difference between these processors and, let's say, a Leon processor, which is totally rad hard, is the performance that you can get out of them. We're looking at those two processors there, the 8548, looking at 5 gigaflops, the 7448, maybe 10, getting towards 10 gigaflops. These two here are above 10, and then the LS1046, that's 30 gigaflops of performance, processing performance that you can have on your satellite. And David Gambo was speaking earlier on today about having that processing performance on the satellite. That gives you advantages that you don't need your data link to be overloaded to the Earth. You've got much more real-time control, so real-time control for robotics on the satellite is possible. And you can do real-time processing, let's say for synthetic aperture signals. You don't need to send the raw data down to the Earth to have it analyzed. It can be done on the satellite. And then if it's done on the satellite, if you see something interesting in real time, you say, oh, that's interesting, maybe we can take a zoom in on that. So that's the advantage. I mean, I heard that some experiments, some NASA experiments were being canceled because they were producing too much data and there wasn't enough bandwidth on the data link to the Earth to make the experiment useful. Now, doing some kind of data compression using a high-power processor is a good idea. And there's a success story for the PC7448. That's gone onto a weather satellite. And this particular processor is part of an imaging system. It's looking at the lightning that occurs on the Earth and getting information about weather patterns from that. So here's another part of our portfolio. This is RF gain blocks, power amplifiers. And this is a mix of full space-grade parts, so ceramic package and the full screening, and some upscreened parts, some plastic upscreened parts. I've got one slide that shows you how we're trying to match up these differing requirements from new space and traditional space markets. Here's our power offer, and again, it shows that we have traditional space parts with ceramic packages, point-of-load circuits, and FETs for DC switching. You see there's a ceramic package version available, but also we have the standard plastic package version available with extra qualification, extra screening for space COTS applications. And that's what we try to do. Sorry, this one. Okay. Oh, sorry. There's one slide gone off there. But so I'll have to describe the slide to you now. The slide was showing you how we adapt between the requirements for space COTS and traditional space. We have two options. We either don't do as much screening for a traditional space part, or we upscreen an industrial space part. So they're the two options, and that's what we try to do for our individual customers. It's the same silicon, but there's a different level of screening involved. The one thing that is kind of always required by space COTS application, new space application, is a knowledge of the radiation performance. So that's really a prerequisite for a part to be in the space COTS arena. It needs to have a good radiation performance. And as long as it's got that, then which screening is done, which qualification is done, depends a lot on the actual application and the orbit and the lifetime of the mission. So here's the summary. From my view, it seems that the traditional space market is quite structured. Every company in that food chain has good experience and knows a lot about the market that it's particularly in. There is, for some of those companies, particularly the tier twos, there's some reliance on central funding. So some companies are really dependent on the funding of IESA, and so they really need to make sure that they get the next project through IESA. The traditional space standards, they're well known. You've got documents, QMLB, ESCC 9000, they're very well known. But could be for newer companies a slight barrier to entry to that market. Now, the new space standards, there's no new space standard. As I said, radiation performance is probably the only requirement that I'm aware of that's applicable to all space applications. And so it's very much on a case-by-case basis. And so we can tailor the amount of screening that's done for a particular application depending on requirements of it. And so, as I showed you the example of Teledyne Microwave, outsourcing has provided companies to expand their portfolio, to expand their area of interest. And from my point of view, as a component manufacturer, we need to adjust to these different quality levels that are being required by our customers. So that's my summary. Thank you very much for listening, and
thank you very much indeed, Andrew.
thank you.
I'd like to request Rahul Arya to please present a small token of appreciation to Andrew Glascott-Jones.
Thank you. Thank you very much. Oh yeah, we need to go to the middle. Thank you. Thank you very much.